Look up at the night sky, and what do you see? A vast, glittering expanse of stars, galaxies, and cosmic wonders stretching beyond comprehension. But here's the thing, what we're seeing isn't just random. The universe has a structure, a pattern, almost like it's following some grand, invisible blueprint. And that raises a question so profound it's haunted scientists and dreamers for centuries. Why does the universe look like this? Why do galaxies cluster in sprawling webs? Why do stars arrange themselves in spiraling arms? And what does it all mean for us, tiny observers on a pale blue dot? This isn't just about distant lights in the dark. It's about the very fabric of reality itself, the way the universe looks, its shape, its structure, even the way matter is scattered across the cosmos holds clues to the deepest mysteries of existence. From the explosive birth of space and time in the Big Bang to the strange, invisible forces shaping everything we see, the story of the universe's appearance is a puzzle with pieces we're still trying to fit together. And every discovery, every new glimpse into the cosmos, brings us closer to understanding our place in this grand, unfolding story. So let's take a journey not just through space, but through time, through the very laws that govern reality. We'll unravel how galaxies form, why the cosmos isn't just a uniform sea of stars, and what dark matter and dark energy have to do with the universe's eerie, beautiful structure. Along the way, you'll see how humanity's quest to understand the cosmos has reshaped science, philosophy, and even our sense of wonder. Because when you stare into the night sky, you're not just looking at points of light, you're looking at a cosmic mystery billions of years in the making. And by the end of this, you'll never see the universe the same way again. To truly grasp why the universe looks the way it does, we have to rewind the clock, way back to the very beginning. Picture a moment before stars, before galaxies, before even light itself had a chance to travel. The Big Bang didn't just create space, it set the stage for everything we see today. But here's the twist, the early universe wasn't this perfectly smooth soup of matter. Tiny fluctuations smaller than a single atom were baked into the fabric of reality. These microscopic wrinkles held the seeds of destiny, the future homes of galaxies, the voids between them, even the vast cosmic web that connects it all. Now, fast forward hundreds of millions of years, gravity, that relentless sculptor, got to work. Those tiny density variations started pulling matter together, like invisible hands gathering cosmic dust. But gravity didn't act alone. Dark matter, the universe's mysterious scaffolding, played a silent, crucial role. While we can't see it directly, its gravitational grip shaped the distribution of galaxies into those intricate, thread-like patterns we observe today. Imagine pouring syrup onto a pancake and watching it spread in branching veins. That's dark matter weaving the universe's largest structures. And then there's dark energy, the enigmatic force pushing the cosmos apart. Without it, gravity might have eventually pulled everything back into a single point. Instead, dark energy ensures the universe keeps expanding, stretching those galactic threads ever farther apart. It's a cosmic tug of war, gravity pulling matter together, dark energy pushing space itself apart. The result, a universe that looks both organized and wild, with galaxies clustered like cities in a vast, ever-growing desert. But here's what's even more astonishing. The patterns we see aren't random. They're echoes of the universe's infancy, amplified over billions of years. When astronomers map thousands of galaxies, they're essentially reading a fossil record of the cosmos. Each cluster, each filament, Each empty void tells a story about how the universe grew up. And just like tree rings reveal a tree's history, the universe's structure holds clues about its past, its present, and maybe even its ultimate fate. So the next time you gaze at the night sky, remember, you're not just seeing stars, you're witnessing the aftermath of a 14 billion-year construction project shaped by forces we're only beginning to understand. The universe didn't just happen to look this way, it was built, piece by piece, by the laws of physics themselves. And that means every glittering dot above you is part of a far grander design, one we're still unraveling. If you could shrink the universe down to the size of a room and peer inside, you wouldn't see chaos, you'd find an intricate tapestry, a sprawling network of glowing threads connecting islands of galaxies across unfathomable distances. This is the cosmic web, the universe's grand architectural design. Think of it like the nervous system of the cosmos, with galaxies clustered along delicate filaments, separated by vast, empty voids so large they could swallow thousands of Milky Ways. But how did this web form, and what keeps it holding together? The answer lies in an invisible hand guiding the universe's growth. Dark matter is the unseen architect behind this structure. While ordinary matter, the stuff of stars, planets, and us, makes up less than 5% of the universe, dark matter outweighs it 5 to 1. Its gravity acts like an invisible framework, pulling gas and dust into dense knots along its threads. Simulations show this process in stunning detail. Supercomputers model how dark matter's gravitational pull sculpts the cosmos over billions of years, creating a web eerily similar to what telescopes observe. Without dark matter's scaffolding, galaxies would be scattered like lonely islands adrift in an endless sea. But the cosmic web isn't just a static blueprint, it's dynamic, evolving. As galaxies form along these filaments, they're funneled toward intersections where clusters grow into dense metropolises of stars. Meanwhile, the voids between filaments stretch emptier over time, as if the universe itself is exhaling. This isn't just a pretty pattern, it's a record of cosmic history. By mapping the web, astronomers can trace how gravity and dark energy have shaped the universe from its infancy to today. What's even more remarkable is how fragile this web seems, yet how enduring. The threads are tenuous, with galaxies spaced millions of light-years apart, held together by forces we can't see. And yet, this delicate structure has persisted for billions of years, a testament to the delicate balance between gravity's pull and dark energy's push. The cosmic web isn't just the universe's skeleton, it's a living, breathing map of existence itself, revealing secrets about where we came from and where everything is headed. Imagine trying to build a towering skyscraper, only to realize the blueprints show just the windows and doors, none of the steel beams holding it up. That's essentially the predicament astronomers faced when they first noticed galaxies spinning far too fast for the amount of visible matter they contained. Stars on the outer edges should have been flung into space like riders on an out-of-control merry-go-round, yet they clung tightly to their galactic orbits. This cosmic conundrum was our first clue that something invisible, something massive, was lurking in the shadows, its gravitational grip keeping everything together. That something is dark matter, the universe's hidden scaffolding. The evidence for dark matter isn't just limited to galaxy rotations. Look at how light bends around massive galaxy clusters, warping like a funhouse mirror. This phenomenon, called gravitational lensing, reveals that there's far more mass distorting spacetime than what we can see. It's as if you tossed a pebble into a pond and the ripples were 10 times larger than the pebble itself, a sure sign something unseen is amplifying the effect. Even the cosmic microwave background, the afterglow of the Big Bang, bears the fingerprint of dark matter's gravitational influence, with temperature fluctuations that only make sense if this mysterious substance exists. But here's what's truly mind-bending. Dark matter doesn't just explain how galaxies hold together. It explains why they're arranged the way they are. In a universe with only ordinary matter, galaxies would be scattered randomly, like sprinkles haphazardly tossed on a cupcake. Instead, we see them clustered along filaments, drawn into vast superclusters with enormous voids between them. Computer simulations show this precise pattern emerging only when dark matter's gravitational pull is factored in, guiding ordinary matter into the universe's grand design like an invisible hand arranging stars on a cosmic chessboard. And yet, for all its importance, dark matter remains elusive. It doesn't emit, absorb, or reflect light. It interacts with gravity and nothing else. Scientists have spent decades searching for it directly, using detectors buried deep underground to shield from interference, or watching for faint signals in space. So far, dark matter keeps its secrets, revealing itself only through its gravitational effects. Some theories suggest it could be made of undiscovered particles, while others propose modifications to our understanding of gravity itself. But one thing's certain, without dark matter, the night sky would be unrecognizable, a dim, sparse expanse missing the brilliant structures we take for granted. The more we learn about dark matter, the more we realize how fundamental it is to the universe's very identity. It's not just an add-on to cosmic physics, it's the framework upon which everything visible is built. From the smallest dwarf galaxy to the largest supercluster, dark matter's gravity wrote the rules of the cosmic game. And as we peer deeper into the shadows, we're not just searching for missing matter, we're uncovering the hidden blueprint of reality itself. If dark matter is the invisible scaffolding holding the universe together, dark energy is the mysterious force tearing it apart, an anti-gravity pushing space itself to expand faster and faster. Picture blowing up a balloon with dots on its surface. Now imagine the balloon inflates so rapidly that soon those dots can no longer see each other. That's the unsettling future dark energy is crafting for our cosmos. The story of its discovery reads like a cosmic detective novel. In the late 1990s, astronomers were studying distant supernova exploding stars so bright they can outshine entire galaxies. These stellar explosions serve as cosmic mile markers, letting scientists measure how fast the universe has expanded over billions of years. But something wasn't right. Instead of finding the expansion slowing down as gravity should dictate, they saw it speeding up. It was as if someone had stepped on the universe's accelerator pedal, flinging galaxies apart at ever-increasing velocities. This revelation flipped cosmology on its head. Up until then, most scientists assumed gravity would eventually win, either pulling everything back in a big crunch or settling into a gentle coast. But dark energy changed the script, accounting for roughly 68% of the universe's total energy. It's now the dominant force shaping cosmic destiny. Unlike gravity, which weakens with distance, dark energy's push grows stronger as space stretches, making its effects more dramatic over time. What could possibly be driving this runaway expansion? The leading theory points to the vacuum of space itself, not empty, but crackling with a strange, repulsive energy woven into the fabric of reality. Einstein once proposed a similar idea called the cosmological constant, though he later dismissed it as his greatest blunder. Turns out he might have been onto something after all. The implications are staggering. If dark energy continues unchecked, galaxies beyond our local group will eventually vanish over the cosmic horizon, their light stretched beyond detection. Distant civilizations of the future might gaze at their night sky and see only darkness, their universe reduced to an island of lonely stars. But dark energy isn't just a cosmic wrecking ball, it's also a time capsule. By measuring its effects, we're glimpsing the universe's fate written in the stretching of space-time itself. Yet for all we've learned, dark energy remains one of physics' deepest enigmas. Is it truly constant, or could it evolve over time? Could it someday rip apart even atoms themselves in a Big Rip scenario? Each new observation peels back another layer of the mystery, reminding us that the universe is far stranger and more wondrous than we ever imagined. The universe wasn't always this grand cosmic tapestry we see today. It began as something unimaginably small, hot, and dense. Picture squeezing everything that exists, every galaxy, every star, every atom, into a space smaller than a single grain of sand. Then, in an instant, it exploded outward, not into empty space, but creating space itself as it expanded. This was the Big Bang, the moment time and reality as we know it began. But here's what's truly fascinating. That initial explosion didn't just fling matter randomly into the void. It planted the seeds for the universe's entire structure, setting in motion a chain of events that would eventually lead to galaxies, stars, and even us. For the first few moments, the universe was so hot and dense that not even atoms could form. It was a seething ocean of particles, protons, electrons, photons, all crashing into each other at unimaginable speeds. Light couldn't travel freely. It was trapped in this chaotic soup, bouncing endlessly. Then, around 380,000 years after the Big Bang, something extraordinary happened. The universe cooled enough for electrons to finally latch onto protons, forming the first hydrogen atoms. This cosmic recombination released the trapped light, sending it streaming across the universe in all directions. That ancient glow, now stretched into microwaves by the expansion of space, is what we detect today as the cosmic microwave background, a baby picture of the universe frozen in time. But look closer at that snapshot, and you'll notice something peculiar. The cosmic microwave background isn't perfectly uniform. Tiny variations in temperature, fractions of a degree, reveal regions that were slightly denser than others. These minuscule fluctuations might seem insignificant, but they were the universe's first blueprints. Over billions of years, gravity amplified those tiny differences, pulling matter together into clumps that would become the first stars, then galaxies, and eventually the vast cosmic web we see today. It's like blowing up a balloon with faint pencil marks on it. As the balloon expands, those marks grow into bold, unmistakable patterns, and here's where dark matter re-enters the story. Those early density variations weren't just in ordinary matter. They were imprinted even more strongly in dark matter, which doesn't interact with light or other forces. While ordinary matter was buffeted by radiation pressure, dark matter could quietly gather under its own gravity, forming invisible halos that would later anchor galaxies. Without this unseen scaffolding, the universe might have remained a featureless haze, never giving rise to the glittering structures we observe. The transition from that smooth, hot beginning to the structured cosmos we inhabit is one of the most astonishing transformations in nature. From quantum ripples to galactic superclusters, the universe's story is written in the interplay of gravity, dark matter, and the relentless expansion of space. Every galaxy, every star, every planet is a direct result of those first moments, a cosmic legacy written in the fabric of reality itself. So when you look up at the night sky, you're not just seeing distant objects. You're witnessing the echo of creation, a story 14 billion years in the making. The universe didn't just expand after the Big Bang. It exploded outward at a speed so mind-bending it defies intuition. In less than a trillionth of a second, space itself stretched by a factor of at least 10 to the power of 26. That's like inflating a grain of sand to the size of our entire observable universe in the blink of an eye. This runaway expansion, called cosmic inflation, wasn't just a faster version of the steady growth we see today. It was a violent, exponential surge that shaped everything from the largest galaxy clusters to the tiniest quantum ripples in spacetime. Why does this matter? Picture a balloon covered in wrinkles. If you inflate it slowly, those creases remain. But if you blow it up suddenly, snap, the surface becomes smooth. That's precisely what inflation did to the infant universe. Before inflation, spacetime might have been a chaotic mess of irregularities, with some regions denser or hotter than others. But inflation's lightning-fast expansion stretched those wrinkles so thin that the cosmos became eerily uniform on large scales. This explains why the cosmic microwave background, the afterglow of the Big Bang, has almost the same temperature in every direction we look, down to variations of just 1 part in 100,000. But inflation didn't just erase imperfections, it also planted the seeds for new ones. Quantum fluctuations, those tiny jitters inherent to reality at the smallest scales, got stretched to cosmic proportions during this explosive growth. These microscopic ripples became the density variations that gravity later amplified into galaxies and galaxy clusters. It's as if the universe took a deep breath during inflation, holding onto imperfections that would one day bloom into the cosmic web we see today. Without inflation, those initial irregularities might have been too weak to ever form the structures that make our universe so rich and textured. The evidence for inflation isn't just theoretical. Scientists have searched for its fingerprints in the polarization patterns of the cosmic microwave background, subtle swirls in the ancient light that could only have been imprinted by gravitational waves from inflation's violent expansion. While the data isn't conclusive yet, the fact that the universe looks so uniform on large scales, with no jagged edges or abrupt temperature changes, strongly supports the idea. Inflation elegantly solves what cosmologists call the horizon problem, the puzzle of why regions of the universe now separated by billions of light years appear so similar, even though they were never close enough to exchange heat or information. Yet for all its success, inflation raises its own mysteries. What triggered it? What stopped it? Some theories suggest it was a phase transition, like water freezing into ice, where the energy trapped in an exotic early state of the universe suddenly converted into expansion. Others propose that inflation might not be a one-time event, that our universe is just one bubble in an eternally inflating multiverse, where new cosmic domains sprout endlessly. These ideas push the boundaries of physics, hinting at forces and fields we've yet to discover. Inflation's legacy is written across the sky. Every galaxy, every filament of the cosmic web, even the vast emptiness between them, traces back to those first instants of exponential growth. It's a reminder that the universe's largest structures were born from the smallest quantum whispers, and that the forces shaping reality operate on scales both unimaginably vast and infinitesimally tiny. So when astronomers map the heavens, they're not just charting stars and gas. They're reading the story of inflation, the universe's first and most dramatic growth spurt. Galaxies aren't just scattered randomly across the cosmos, they are organized, evolving entities, each with its own history written in stars, gas, and dark matter. To understand how these cosmic cities form, we have to start with their invisible foundations, dark matter halos. These enormous, ghostly structures, weighing hundreds of trillions of times more than our Sun, act like gravitational wells, pulling in ordinary matter over billions of years. Picture a spiderweb catching droplets of water. Dark matter's unseen threads gather gas and dust, setting the stage for galaxies to grow. but gas alone doesn't make a galaxy. It has to cool down, condensing into dense pockets where stars can ignite. In the early universe, this process was slow and delicate. Hydrogen atoms, excited by the energy of the young cosmos, had to shed heat by emitting light, allowing them to clump together. The first stars flickered to life inside these cooling clouds, their radiation carving out bubbles in the surrounding gas. Over time, gravity took over, pulling more material into these nascent galaxies, fueling generations of new stars. Some galaxies, like our Milky Way, grew steadily, their gas settling into elegant spiral arms. Others, through violent collisions, morphed into giant ellipticals, their stars orbiting in chaotic, swirling dances. Mergers play a crucial role in shaping galaxies. When two galaxies collide, their stars rarely crash. Space is too vast, but their gas clouds slam together, triggering bursts of star formation. Dark matter halos intertwine, reorganizing the galactic structure. Some mergers create monstrous ellipticals, while others strip galaxies of their gas, leaving them red and dead, with no fuel left to form new stars. Our own Milky Way bears the scars of past mergers, with streams of stars tracing the remains of smaller galaxies it swallowed long ago. Yet not all galaxies follow the same path. Dwarf galaxies, faint and diffuse, often orbit larger ones like fireflies around a lantern. Their dark matter halos may have protected them from being torn apart, preserving clues about the universe's early days. At the other extreme, supermassive black holes lurking in galactic centers can blast out jets of energy, heating surrounding gas and shutting down star formation entirely. The interplay of these forces, gravity, gas cooling, mergers, and black holes, creates the stunning diversity of galaxies we observe. Every galaxy is a time capsule, holding secrets about the conditions that shaped it. By studying their structures, ages, and motions, astronomers piece together the story of cosmic evolution, from the first flickers of starlight to the majestic spirals and ellipticals we see today. The universe doesn't just build galaxies, it sculpts them, endlessly reshaping the cosmic landscape. And in that grand design, each galaxy, from the smallest dwarf to the largest cluster, plays a part in the unfolding story of the cosmos. Gravity is the silent artist of the cosmos, patiently sculpting the universe over billions of years. While other forces govern atoms or light, gravity works on the grandest scales, weaving matter into the vast cosmic web we see today. It all starts with Newton's simple but profound realization that every bit of matter in the universe pulls on every other bit, no matter how distant. An apple falls to Earth, planets orbit the sun, and galaxies dance in clusters, all governed by this invisible force. But gravity's true power lies in its persistence. Unlike a magnet that can be blocked or a nuclear force that fades at short distances, gravity never stops, never weakens to zero. Over cosmic time, even its faintest whisper adds up, turning random clumps of gas into glittering cities of stars. Einstein reshaped our understanding of gravity, revealing it not as a force but as the curvature of spacetime itself. Picture placing a bowling ball on a trampoline. The depression it creates is like a star warping space around it. Roll a marble nearby and it spirals inward, tracing the curve. That's how planets orbit stars and stars orbit galactic centers. But on cosmic scales, this curvature does something extraordinary. It molds the distribution of matter itself. Regions slightly denser than their surroundings, thanks to those primordial quantum fluctuations, become gravitational wells, pulling in more gas, more dark matter, more everything. Over eons, these grow into galaxies, while the emptier regions stretch into vast voids. The universe's structure is a record of gravity's tireless work. Galaxy clusters, the largest bound structures in existence, are held together by gravity's unbreakable grip. Some contain thousands of galaxies, each with billions of stars, all orbiting a common center like bees around a hive. Filaments of dark matter trace the outlines of this web, with galaxies strung along them like pearls on a necklace. Even the voids, those enormous, seemingly empty regions, are shaped by gravity, or rather by its absence. Matter has been steadily drained from these areas over billions of years, sucked toward the denser filaments and nodes, yet gravity doesn't act alone. It's locked in a cosmic tug of war with dark energy, which pushes space apart even as gravity pulls matter together. This delicate balance defines the universe's appearance. Too much gravity and everything would have collapsed back into a singularity long ago. Too much dark energy and matter would never have clumped enough to form stars or planets. We live in the narrow window where these forces create a universe rich in structure, one where gravity's patient craftsmanship can build galaxies, but dark energy ensures they don't overcrowd the cosmic stage. The beauty of gravity lies in its universality. The same force that makes a pencil roll off your desk also orchestrates the dance of galaxy superclusters. It's why the night sky isn't a uniform glow but a tapestry of light and dark, of clusters and voids, of chaos and order. Every galaxy, every star, every planet exists because gravity never stops working, gathering dust into worlds and worlds into cosmic masterpieces. For all its grandeur, the universe is strikingly empty when it comes to the stuff we can actually see. The atoms, molecules, and particles that make up stars, planets, and life itself. This ordinary matter, known to scientists as baryonic matter, accounts for just 5% of the cosmos. The rest is a cryptic mix of dark matter and dark energy, invisible to our telescopes yet dictating the universe's structure. But here's the twist: that tiny 5% is responsible for all the light, color, and complexity we perceive. Without it, the cosmos would be a shadowy void, its beauty hidden in darkness. Baryonic matter gets its name from protons and neutrons, particles called baryons that form the cores of atoms. Alongside electrons, they build everything tangible, from the iron in your blood to the neon glow of distant nebulae. When we gaze at the Milky Way's shimmering band or the Orion Nebula's swirling hues, we're seeing baryonic matter in action. Gas clouds collapse under gravity, igniting stars that forge heavier elements in their cores. Supernova blast those elements into space, seeding new generations of stars and planets. It's a recycling process spanning billions of years, with baryonic matter as both the raw material and the artist's brush. Yet this visible universe doesn't exist in isolation. Dark matter's gravitational pull guides where baryonic matter accumulates, like an invisible hand molding clay. Without it, galaxies would never have formed their stars and gas would have scattered like leaves in the wind. But dark matter's halos provided the gravitational anchors, gathering baryonic gas into dense enough clouds to spark star formation. The cosmic web's luminous strands, the glittering arms of spiral galaxies, even the vast clusters where hundreds of galaxies orbit like bees around a hive, all owe their existence to this partnership between the seen and unseen. The dance between baryonic matter and dark energy is equally fascinating. As dark energy accelerates the universe's expansion, it stretches space itself, thinning out the baryonic gas between galaxies. Over time, this will make star formation rarer, leaving galaxies isolated in an ever-darkening cosmos. Yet for now, baryonic matter thrives in pockets where gravity still holds sway, lighting up the darkness with stars and supernova. It's a fleeting era in cosmic terms, but one that gives us everything we know: the warmth of sunlight, the glow of nebulae, even the conditions for life. What's truly remarkable is how much complexity arises from such a small fraction of the universe's contents. The iron in your blood, the silicon in Earth's crust, the oxygen you breathe, all were forged in the hearts of stars, scattered across space and gathered anew by gravity's patient pull. Every photo of a distant galaxy, every spectrum of starlight, every exoplanet discovery is a testament to baryonic matter's outsized role. It may be just 5% of the cosmic budget, but it's the part that makes the universe visible, vibrant, and alive. And that's a reminder of how special and how rare our luminous corner of reality truly is. One of the most puzzling mysteries in modern cosmology isn't about distant galaxies or dark matter. It's about a single number. The Hubble constant, which tells us how fast the universe is expanding, should be straightforward to measure. But here's the catch: depending on how you calculate it, you get different answers. This discrepancy, known as the Hubble Tension, has astronomers scratching their heads because it suggests something fundamental in our understanding of the cosmos might be missing or misunderstood. To grasp why this is such a big deal, let's look at the two main ways scientists measure the Hubble constant. The first method relies on the cosmic microwave background, the afterglow of the Big Bang. By studying tiny temperature fluctuations in this ancient light, researchers can extrapolate how fast the universe should be expanding today. These measurements, made with exquisite precision by satellites like Planck, give us a Hubble constant around 67 kilometers per second per megaparsec. That means for every million parsecs of distance, about 3.26 million light-years, a galaxy moves away from us 67 kilometers per second faster. But there's another way to measure the expansion: by observing nearby stars and galaxies directly. Astronomers use standard candles, objects with known brightness like Cepheid variable stars or Type Ia supernova, to gauge cosmic distances. By comparing how fast these objects are moving away from us to how far away they are, they can calculate the Hubble constant independently. The problem: these local measurements consistently land around 73 kilometers per second per megaparsec, noticeably faster than the cosmic microwave background predicts. At first glance, a difference of 6 might not seem like much, but in cosmology, where precision is everything, this gap is enormous. It's like two clocks ticking at slightly different rates over billions of years. Those tiny discrepancies add up to completely different cosmic histories. If both methods are correct, then our assumptions about the universe's composition or behavior must be flawed. Maybe dark energy isn't constant but changes over time. Perhaps there's an unknown particle influencing the expansion rate, or our understanding of gravity needs revising. Some have even speculated that we're seeing evidence of multiple universes, though that remains highly speculative. The Hubble tension isn't just a technical disagreement, it's a potential crack in the foundation of modern cosmology. Resolving it could lead to groundbreaking discoveries, reshaping our understanding of everything from the Big Bang to the universe's ultimate fate. For now, astronomers are refining measurements, searching for hidden biases, and exploring exotic theories. Whatever the answer turns out to be, one thing's certain: the universe still has surprises in store, and the Hubble tension might be our first clue to uncovering them. At the smallest scales imaginable, the universe is never perfectly still. Even in the vacuum of empty space, particles flicker in and out of existence, borrowing energy from nothingness before vanishing again. These quantum fluctuations might seem insignificant after all. They happen on scales trillions of times smaller than an atom. But in the early universe, they held the key to everything we see today. When inflation stretched the cosmos in those first fractions of a second, it didn't just smooth out wrinkles, it amplified these quantum jitters, blowing them up to cosmic proportions. Imagine scribbling tiny dots on a deflated balloon, then inflating it to the size of a stadium. Those once invisible marks would now stretch across vast distances. That's exactly what happened to quantum fluctuations during inflation. Regions that were ever so slightly denser due to these random variations became the gravitational seeds around which galaxies would later form. The cosmic microwave background is our clearest snapshot of these primordial ripples. That faint afterglow from the universe's infancy shows temperature variations of just 1 part in 100,000, barely more than a whisper against the cosmic background. But those subtle differences in heat correspond directly to density variations, revealing where matter had begun clumping together. It's like looking at a black and white photo and realizing the faintest shades of gray outline the blueprint for every galaxy cluster in existence. Gravity did the rest. Over hundreds of millions of years, it sculpted those subtle overdensities into vast cosmic structures. Dark matter's invisible scaffolding provided the framework, while ordinary matter, drawn in by gravity's pull, condensed into stars and galaxies. The largest galaxy clusters we see today trace back to the luckiest quantum fluctuations, regions where randomness conspired to create slightly deeper gravitational wells. What's astonishing is how perfectly balanced these fluctuations were. If they'd been much stronger, matter would have collapsed too quickly, forming monstrous black holes instead of galaxies. Much weaker, and gravity wouldn't have had enough to work with, leaving the universe a near-featureless void. The fact that we exist in a cosmos filled with galaxies, planets, and life suggests these quantum seeds were tuned to precisely the right amplitude, not too hot, not too cold, but just right for complexity to emerge. This connection between quantum mechanics and cosmic structure is one of the most profound insights in modern cosmology. The same physics governing particles smaller than we can conceive also shaped the largest structures in existence. From subatomic randomness to galactic superclusters, the universe's structure is a testament to how microscopic beginnings can have cosmic consequences. And that means every galaxy, every star, every planet owes its existence to quantum uncertainty. A reminder that even in the vastness of space, the smallest things matter most. What if our universe isn't the only one? Imagine a cosmic ocean where each bubble is an entirely separate universe, with its own laws of physics, its own history, maybe even its own version of reality. This isn't science fiction, it's a serious scientific hypothesis called the Multiverse Theory, and it could radically reshape how we understand existence itself. One of the most compelling arguments for the multiverse comes from inflation, that rapid expansion of the early universe we discussed earlier. Some versions of inflation suggest it never truly stopped. Instead, our universe might be just one pocket where inflation slowed enough for stars and galaxies to form, while elsewhere, space continues expanding exponentially. In this eternal inflation scenario, new bubble universes pop into existence endlessly, each with random properties. Most might be sterile, devoid of the delicate balance needed for life. But statistically, a few would land in the sweet spot like ours. String theory adds another layer to the mystery. To make the math work, this framework requires extra dimensions beyond the 3 we experience, possibly 6 or 7 more. These hidden dimensions could curl up in countless configurations, each producing a universe with different physical constants. In one, gravity might be stronger, crushing atoms instantly. In another, electromagnetism could be too weak to form molecules. Ours, by sheer chance, has the right recipe for complexity. The multiverse isn't just a wild guess, it could solve some of cosmology's biggest puzzles. Take the fine-tuning problem. Why are the fundamental constants so perfectly balanced for life? If infinite universes exist with every possible variation, it's no surprise we find ourselves in one where conditions allow us to exist. It's like walking into a library with every conceivable book. You'd naturally pick up the one in your language. critics argue the multiverse is untestable, more philosophy than science. But researchers are hunting for clues. Some propose that collisions between adjacent bubble universes might leave imprints in the cosmic microwave background, like bruises on the surface of our cosmos. Others suggest that gravity could leak between universes, subtly altering how galaxies cluster. Even if we never directly observe another universe, its influence might still be detectable. Whether the multiverse is real or not, the idea stretches our imagination to its limits. It forces us to confront the possibility that reality is far stranger and far grander than we ever dreamed. And if it's true, then the mysteries we've been exploring, dark matter, cosmic inflation, even the nature of time, might just be local phenomena unique to our tiny corner of an unfathomable multiverse. The cosmic microwave background isn't just ancient light, it's a time machine. When astronomers point their telescopes at this faint glow, they're peering back to a moment when the universe was a mere 380,000 years old, a cosmic toddler taking its first steps. Back then, the cosmos was a scorching plasma, so hot that electrons couldn't latch onto protons. Light couldn't travel freely. It was trapped in a chaotic dance with charged particles, bouncing endlessly like a pinball. But as the universe expanded and cooled, something remarkable happened. Electrons finally combined with protons to form the first hydrogen atoms, a process called recombination. Suddenly, light broke free, streaming across space in all directions. That burst of radiation, now stretched into microwaves by 14 billion years of cosmic expansion, is what we detect today as the cosmic microwave background. What makes this glow so special isn't just its age, it's the secrets encoded in its subtle variations. To the naked eye, the CMB looks nearly uniform, a bland sea of microwaves. But precision instruments like the Planck satellite reveal tiny temperature differences, fluctuations as small as 1 part in 100,000. These aren't random. They're frozen imprints of the universe's earliest density variations, the gravitational seeds from which galaxies would later grow. Regions slightly hotter than average were denser, packed with more matter. Cooler spots were emptier. Over billions of years, gravity amplified these differences, pulling matter into the cosmic web we see today. The CMB is like a baby photo with the outlines of adulthood already faintly visible. But the cosmic microwave background tells us more than just where matter clumped. It's a ledger of the universe's contents. By analyzing the CMB's patterns, scientists have calculated the precise mix of ordinary matter, dark matter, and dark energy. The math is stunning: 5% atoms, 27% dark matter, and 68% dark energy. These numbers don't just match observations of galaxies and supernova, they've become the bedrock of modern cosmology. The CMB also carries echoes of the universe's earliest moments. Faint polarization patterns in the light may trace gravitational waves from cosmic inflation, offering a glimpse into the universe's first trillionth of a second. Perhaps most astonishing is how this fossil light connects the largest and smallest scales of reality. The fluctuations we see originated as quantum jitters, microscopic randomness blown up to cosmic proportions by inflation. The same physics governing particles smaller than atoms shaped the distribution of galaxy clusters, and because the CMB comes from everywhere at once, it lets us measure the universe's geometry. Is space flat, curved, or closed? The angles between temperature fluctuations say it's flat to within a razor-thin margin, a finding that reshaped our understanding of cosmic destiny. Every time we map the cosmic microwave background, we're not just studying light, we're reading the universe's autobiography written in the afterglow of creation. And with each new observation, we uncover another page revealing how a fiery, dense beginning gave rise to the rich, structured cosmos we call home. Imagine holding a map so vast it charts millions of galaxies, each one a glowing pinprick tracing the outlines of an invisible cosmic skeleton. That's exactly what projects like the Sloan Digital Sky Survey have given us, an atlas of the universe on the grandest scales. By meticulously recording the positions and distances of galaxies across enormous swaths of space, these surveys reveal something astonishing. The universe isn't just sprinkled randomly with stars and galaxies. Instead, it's structured like a colossal spiderweb, with galaxies clustered along delicate filaments, intersecting at massive nodes, and separated by vast, empty voids so large they could swallow thousands of Milky Ways whole. These maps aren't just pretty pictures, they're forensic evidence of cosmic history. Every filament, every cluster, every void tells a story about how gravity and dark energy have shaped the universe over billions of years. When astronomers analyze the patterns, they're essentially reading a cosmic fingerprint left by dark matter's invisible hand. The way galaxies are distributed matches eerily well with supercomputer simulations of dark matter's gravitational influence, confirming that this mysterious substance is the hidden framework upon which everything visible is built. Without these surveys, we'd be like detectives trying to solve a mystery with only half the clues. But how do you even begin mapping something as unimaginably huge as the observable universe? The Sloan Digital Sky Survey used a dedicated telescope to capture light from millions of galaxies, measuring their redshifts, how much their light stretches as the universe expands, to calculate their distances. Over time, these data points coalesced into a three-dimensional model, revealing structures so vast they defy human intuition. Some filaments stretch over 1 billion light-years, weaving through the cosmos like rivers of galaxies. The sheer scale of these features hints at the patient, relentless work of gravity, pulling matter together over cosmic timescales. What's even more remarkable is how these maps capture the universe in motion. By comparing galaxy positions at different distances, and thus different eras in cosmic history, astronomers can watch the cosmic web evolve. Younger regions show galaxies still falling into filaments, while older clusters sit at the intersections, having grown fat on mergers and acquisitions. The voids, meanwhile, grow emptier over time as gravity steadily drains matter toward the web's dense threads. It's a dynamic, ever-changing structure, with dark energy subtly tilting the balance by pushing galaxies apart faster over time. These surveys also solve a curious puzzle: why galaxies sometimes move in unexpected ways. While the universe's expansion carries most galaxies apart, some show peculiar velocities, drifting toward dense regions like moths to a flame. These motions betray the gravitational pull of unseen mass, dark matter's unmistakable tug. By tracking these flows, astronomers can pinpoint where mass hides, even when it doesn't emit light. It's like watching leaves floating on a river to deduce the underwater currents guiding them. The legacy of these mapping projects goes far beyond cataloging galaxies. They've transformed cosmology from theoretical speculation into precise science, providing hard data to test our models of cosmic evolution. Future surveys, like the upcoming Euclid mission, will extend these maps deeper into space and further back in time, probing the universe's adolescence to understand how the cosmic web first took shape. Each new map adds another layer to our understanding, revealing not just where things are in space, but how they got there and where they're headed next. So the next time you see an image of the cosmic web, remember, you're not just looking at a snapshot of the universe. You're seeing the culmination of 14 billion years of gravitational sculpting, dark matter's invisible architecture, and dark energy's relentless push. It's a reminder that the night sky isn't just a collection of stars, it's a dynamic, evolving masterpiece, and we're only just beginning to trace its brushstrokes. The universe isn't just expanding, it's hurtling toward an unknown fate, and the forces shaping its destiny are locked in an invisible tug of war. On one side, gravity pulls matter together, trying to slow the expansion. On the other, dark energy pushes space apart, accelerating the cosmos toward an uncertain future. Depending on which force wins, the universe could face dramatically different endings. One possibility is the heat death, a slow, quiet fade into darkness. Imagine a cosmos where galaxies drift so far apart that their light can no longer reach one another. Stars burn out, black holes evaporate, and the universe becomes a vast, cold graveyard, a place where even time itself loses meaning. This isn't fire and fury. It's the universe winding down like an old clock, its energy spread so thin that nothing new can ever begin. But there's another, more violent scenario, the Big Rip. If dark energy grows stronger over time, it could eventually overpower every force holding the universe together. First, galaxy clusters would tear apart, then individual galaxies. Stars would be ripped from their orbits, planets shredded, and even atoms torn asunder. In the final moments, spacetime itself would rupture, leaving behind a fragmented, lifeless void. The Big Rip isn't just an ending, it's a cosmic demolition where the fabric of reality is pulled apart at the seams. The difference between these fates hinges on dark energy's nature. Is it constant, as Einstein's cosmological constant suggests, or does it intensify, growing stronger as the universe expands? Right now, observations lean toward a heat-death scenario, but the margin is slim. If dark energy's strength changes even slightly over billions of years, it could tip the scales toward catastrophe. There's also the ghost of an older idea, the Big Crunch. Before dark energy's discovery, many scientists thought gravity might eventually reverse the expansion, pulling everything back into a singularity, a mirror image of the Big Bang. But current evidence suggests this is unlikely unless dark energy somehow weakens or vanishes. Still, the possibility lingers, a reminder that the universe's fate isn't set in stone. What's striking is how deeply interconnected these scenarios are with the universe's structure. The same dark energy stretching the cosmic web today could one day unravel it entirely. The voids between galaxies, already growing emptier, might stretch into absolute isolation. Even the quantum fluctuations that seeded galaxies could be erased, their legacy dissolved in an ever-expanding nothingness. Yet amid these grand cosmic uncertainties, one thing is clear: the universe's fate is being written now, in the subtle interplay of forces we're only beginning to understand. Every measurement of distant supernova, every map of galaxy clusters, brings us closer to answering the ultimate question, not just how the universe began, but how it will end. And that makes our era a remarkable one. We're the first generations to peer into the abyss of deep time and glimpse, however faintly, the final act of the cosmic story. Black holes aren't just cosmic vacuum cleaners, they're master sculptors, shaping galaxies with their immense gravitational pull and violent outbursts. At the heart of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole, millions to billions of times heavier than the Sun. These monsters don't just sit quietly. As matter spirals toward them, it heats up to millions of degrees, glowing fiercely, and sometimes erupting into jets of particles traveling near light speed. These jets can stretch for thousands of light years, carving out bubbles in surrounding gas and effectively putting the brakes on star formation. It's as if the black hole is a capricious artist, sometimes feeding a galaxy's growth, other times halting it in its tracks. Take the galaxy Messier 87, home to one of the most photographed black holes in history. Its jet, visible even in amateur telescopes, pumps energy into the surrounding cluster, heating gas that might otherwise cool and form stars. This creates a feedback loop. The black hole's appetite regulates how many new stars the galaxy can produce. Too much activity, and the galaxy's gas is blown away. Too little, and stars form unchecked. The balance is delicate, and it's why some galaxies are red and dead, their star-making fuel exhausted, while others, like our Milky Way, continue birthing new stars at a leisurely pace. But black holes don't just suppress star formation, they can also trigger it. In the galaxy Centaurus A, shock waves from the black hole's jets compress nearby gas clouds, sparking bursts of star birth like fireworks along the edges of the blast. It's a cosmic paradox. The same force that stifles star formation in one region can ignite it in another. This duality makes supermassive black holes some of the universe's most influential architects, their reach extending far beyond their event horizons. Then there's space-time itself, warped so severely near black holes that light bends into strange loops. This gravitational lensing distorts our view of background galaxies, twisting them into arcs and rings. Even stars orbiting the Milky Way's central black hole behave bizarrely, their paths tracing rosette patterns that confirm Einstein's predictions with stunning precision. These effects aren't just curiosities, they're tools. Astronomers use them to measure black hole masses, test general relativity, and map the invisible structure of galaxies. Perhaps the most astonishing legacy of black holes lies in their role in galaxy evolution. Without them, galaxies might grow too large, too fast, their stars crammed together in unsustainable density. Black holes act like cosmic regulators, their outbursts preventing runaway growth and maintaining the universe's grand diversity of galaxy shapes and sizes. From the tiniest dwarf galaxies to the largest clusters, black holes leave their mark, proving that even the darkest objects in the cosmos can shape its brightest wonders. Here's something that might surprise you. We can only find about half the ordinary matter the universe is supposed to contain. That's right, according to our best calculations of how the cosmos evolved. There should be far more protons, neutrons, and electrons out there than we've actually detected. This isn't about dark matter or dark energy. This is the missing baryon problem, a cosmic case of misplaced atoms that has astronomers scouring the skies for clues. So where could all this matter be hiding? One leading theory points to the vast, almost invisible reservoirs of gas floating between galaxies. Not the dense clouds where stars are born, but an ultra-diffuse plasma, so hot and thin it's nearly undetectable. Scientists call this the warm-hot intergalactic medium, or WIM for short. Imagine a ghostly fog weaving through the cosmic web, so tenuous that a cubic meter of it might contain just a single atom. Yet spread across billions of light-years, it could add up to the missing half of the universe's ordinary matter. Detecting the WIM isn't easy. It doesn't glow like stars or absorb light like cooler gas. Instead, astronomers hunt for its faint fingerprints in the X-ray spectra of distant quasars, the brilliant cores of active galaxies whose light passes through these invisible filaments. Occasionally, the WIM ionized oxygen or nitrogen leaves a subtle absorption line, like a signature in the light. Other times, it betrays its presence by scattering the cosmic microwave background, creating faint distortions in the ancient light. It's painstaking work, like trying to spot a whisper in a thunderstorm, but the WIM isn't the only suspect. Some baryons might be hiding in plain sight, trapped in low-mass galaxies too dim for our telescopes to spot. Others could be tied up in the extended halos of galaxies, vast coronas of hot gas that stretch far beyond the visible starlight. Even the voids, those enormous empty regions between galaxy clusters, might hold traces of this elusive matter, floating in isolated pockets where gravity hasn't yet drawn it into denser structures. Solving this mystery isn't just about balancing the cosmic books. The missing baryons are key to understanding how matter cycles through the universe, flowing from galaxies into intergalactic space and back again. They're the raw material for future stars, the fuel for galactic growth, and a critical piece of the cosmic web's architecture. Without them, our models of galaxy formation and evolution are incomplete, like trying to assemble a puzzle with half the pieces. The hunt for these lost atoms pushes our observational limits, driving innovations in X-ray astronomy and spectroscopy. New telescopes like the upcoming Athena mission could finally bring the WIM into focus, revealing the hidden threads that stitch the universe together. And when we find them, it won't just close a gap in our calculations, it'll deepen our understanding of how the cosmos builds, distributes, and recycles the very stuff we're made of. Because in the end, those missing baryons aren't just numbers on a spreadsheet. They're part of the story of how the universe grew from a hot, dense beginning into the rich, structured tapestry we see today. Every second, trillions of nearly invisible particles pass straight through your body and through the entire Earth without leaving a trace. These are neutrinos, the universe's most elusive ghosts. Billions of them stream from the sun alone, remnants of nuclear fusion in its core, yet you'd need a lead shield light years thick to stop even half of them. Their near weightlessness and refusal to interact with matter make them nearly impossible to detect, yet they've played a crucial role in shaping the cosmos since the very beginning. The story of neutrinos starts just 1 second after the Big Bang, when the universe was still a seething plasma of particles. As protons and neutrons jostled in the intense heat, neutrinos broke free, flooding the young cosmos in a dense fog. For hundreds of thousands of years, they outnumbered atoms by 1 billion to 1, their sheer abundance influencing how matter clumped together in those critical early moments. Even today, this primordial neutrino background permeates space, carrying whispers from the universe's infancy, if only we could read them. But neutrinos don't just linger from the past, they're born in some of the cosmos's most violent events. When a massive star collapses in a supernova explosion, 99% of its energy bursts outward as neutrinos. These particles escape before the shockwave even reaches the star's surface, acting as cosmic messengers announcing the death of a star. In 1987, detectors on Earth caught a handful of neutrinos from a supernova in the Large Magellanic Cloud, marking the first time we'd observed these particles from beyond our solar system. That faint signal, lasting just 13 seconds, confirmed theories about how stars die and how neutrinos help drive these catastrophic explosions. What's truly astonishing is how these ghostly particles shape the universe's largest structures. Though neutrinos barely interact with matter, their tiny mass adds up across the cosmos, subtly tugging on galaxies and dark matter halos. Computer simulations show that without neutrinos' gravitational influence, galaxy clusters would form differently, with matter distributed in slightly denser clumps. It's as if an invisible hand is gently reshaping the cosmic web, its touch so faint we're only now learning to measure it. Detecting neutrinos requires feats of engineering bordering on the absurd. Experiments like IceCube buried deep in Antarctic ice or Super Kamiok and a tank of ultra-pure water beneath a Japanese mountain wait patiently for the rare moment a neutrino collides with an atom. When it happens, the resulting flash of light or burst of particles is a scientific treasure, offering clues about distant supernova, the sun's core, and even the nature of matter itself. Some theories suggest neutrinos could explain why the universe has more matter than antimatter. A tiny asymmetry in their behavior might have tipped the scales in the cosmos's first moments. From the Big Bang to black holes, neutrinos are silent witnesses to the universe's grandest events. They thread through galaxies, pass through stars, and slip through planets as if they weren't there at all. Yet without them, the cosmos as we know it might look entirely different. They're proof that even the most elusive particles can leave an indelible mark on reality, if you know where to look. The universe seems suspiciously well suited for our existence. The gravitational constant, the strength of electromagnetism, even the cosmological constant, all appear fine-tuned to an almost impossible precision. Tweak any of these values slightly and stars wouldn't form, atoms would fly apart, or the cosmos would collapse in on itself. This eerie perfection has led scientists to propose a radical idea. Maybe the universe looks this way because we're here to see it. This is the anthropic principle, a bridge between physics and philosophy that challenges how we interpret cosmic coincidences. At its core, the anthropic principle comes in two flavors. The weak version simply states that we observe the universe the way it is because those are the only conditions where life like ours could arise. It's like a fish marveling at how perfectly water suits its gills, not realizing other environments might host entirely different forms of life. The strong version goes further, suggesting the universe must, in some sense, produce conscious observers. This more controversial take edges into metaphysical territory, implying the laws of physics might be constrained by the necessity of life's existence. Critics argue this sounds like circular reasoning claiming the universe is fine-tuned for life because we're here to observe it. But supporters counter that the odds against our universe's constants being life permitting by pure chance are astronomical. Take the cosmological constant, which governs dark energy's strength. If it were slightly larger, space would expand too fast for galaxies to form. Slightly smaller, and gravity would have crushed everything back into a singularity. The window for life-friendly values is razor-thin, leading some to wonder, is this just luck or is there a deeper reason? One possible explanation lies in the multiverse. If countless universes exist with different physical constants, most would be sterile, but a rare few would, by sheer statistics, land in the life-friendly sweet spot. We'd inevitably find ourselves in one of those habitable bubbles, no matter how improbable. It's like buying every possible lottery ticket eventually. You'll hold a winning number, even if the odds for any single ticket are vanishingly small. This selection effect offers a way to explain fine-tuning without invoking design or purpose. Yet the anthropic principle remains contentious. Some physicists dismiss it as untestable, more philosophy than science. Others see it as a crucial lens for interpreting why our universe looks the way it does. It forces us to confront the limits of observation. We can only study a universe capable of producing observers, which might skew our perspective. Like detectives who only find clues in well-lit areas, we might be missing the bigger picture simply because the rest is inhospitable to our kind of investigation. Whether you find the anthropic principle profound or frustrating, it undeniably reshapes how we think about cosmic mysteries. It reminds us that the universe's appearance isn't just about physics, it's also about the unspoken prerequisites for asking the question in the first place. And that makes our search for understanding not just a scientific endeavor, but a deeply human one. Between the glittering threads of the cosmic web stretch immense deserts of nothingness, regions so empty they could swallow thousands of Milky Ways without a trace. These are cosmic voids, the universe's ghost towns, where matter is almost entirely absent, and galaxies are rare loners drifting in the dark. While galaxy clusters steal the spotlight with their dazzling stellar metropolises, voids tell an equally important story, one of absence, expansion, and the invisible forces sculpting space itself. How do these vast nothingnesses form? It starts with the universe's early unevenness. Those tiny density fluctuations from the Big Bang didn't just create overdensities where galaxies would later bloom, they also carved out underdense regions where gravity had less to work with. As matter flowed toward denser filaments and nodes over billions of years, these underdense pockets were left behind, growing emptier as the cosmic web took shape. Picture water draining from a bathtub. The voids are the patches left dry as liquid rushes toward the drain. But voids aren't just passive leftovers, they're active players in cosmic evolution. Their emptiness creates a unique environment where dark energy's influence is unmasked. Without the competing pull of dense matter, the expansion of space inside voids accelerates faster than anywhere else. Astronomers have measured galaxies at the edges of voids being subtly pushed outward, as if space itself is stretching more aggressively in these barren regions. It's like watching inflating balloons with weak spots. The voids are where spacetime stretches thinnest, revealing dark energy's handiwork in its purest form. The scale of these voids is staggering. The largest, like the Boötes void, span hundreds of millions of light years and contain only a handful of galaxies. If you stood at the center of one, the night sky would appear almost black, with just a few faint smudges breaking the darkness. Yet even these near vacuums aren't completely empty. Trace filaments of gas, a sprinkle of isolated stars, and perhaps wandering rogue planets lurk in the gloom. Some theories suggest voids might even harbor ghost galaxies and dark matter halos that never gathered enough gas to light up with stars. What makes voids truly fascinating is how they mirror the universe's largest structures. Just as galaxy clusters trace the densest knots of the cosmic web, voids outline its empty cells. Together, they form a sort of cosmic foam, with galaxies clinging to the surfaces of bubble-like voids. This foam-like structure is a direct result of gravity and dark energy's tug of war, a three-dimensional fossil record of how the universe has evolved. Studying voids also solves a practical problem. They're ideal laboratories for testing theories of gravity. In dense galaxy clusters, the frenetic motion of stars and gas complicates measurements. But in the serene emptiness of voids, where only a few galaxies drift slowly, any deviations from predicted motions stand out clearly. If alternative theories to Einstein's gravity exist, voids might be where we'll find the evidence. The next time you see a map of the cosmic web, don't just focus on the bright knots of galaxies, pay attention to the black spaces between them. Those voids are more than just gaps. They're the negative space that defines the universe's structure, the silent partners to galaxies in the cosmic dance. Without them, the universe wouldn't look the way it does, and we wouldn't be here to marvel at its design. In the grand tapestry of existence, emptiness is just as meaningful as fullness. The Milky Way isn't drifting through space aimlessly. It's being pulled, along with thousands of other galaxies, toward something massive and unseen. Astronomers call this cosmic tug the Great Attractor, a mysterious region of space roughly 250 million light-years away that's warping the motion of everything around it. Imagine floating down a river only to realize the current isn't random. It's being steered by a hidden waterfall ahead. That's the unsettling sensation scientists face when mapping galaxy motions near this gravitational anomaly. What makes the Great Attractor so puzzling is its location. It lies in the so-called zone of avoidance, an area obscured by the dense dust and stars of our own galaxy's disk. Peering through this cosmic fog is like trying to spot a mountain behind a blizzard. Early observations could only detect the pull, not the source, leaving astronomers to wonder, what could possibly be bending the paths of galaxies on such a colossal scale? The leading theory points to the Norma cluster, a massive gathering of galaxies, along with the surrounding Laniakea supercluster, an immense web of galactic filaments spanning 500 million light-years. Together, these structures might account for some of the gravitational pull, but calculations suggest even they aren't enough to explain the full force dragging us inward. This discrepancy hints at something even more extraordinary: vast concentrations of dark matter, or perhaps entirely unseen structures lurking in the shadows. Some scientists speculate that the Great Attractor could be the heart of an even larger supercluster, one so expansive our current maps only reveal its edges. Others propose it's a junction where multiple cosmic filaments converge, creating a gravitational nexus powerful enough to redirect entire galaxies. The discovery of the Great Attractor has humbled our cosmic perspective. It's a reminder that even with our most advanced telescopes, we're still charting the universe with blind spots. Every time we think we've mapped the largest structures, something like this emerges, challenging our assumptions and revealing how much lies beyond our current view. The Great Attractor isn't just a destination, it's a signpost pointing toward the next frontier of cosmic exploration, where the answers might reshape our understanding of the universe's grand design. Galaxy clusters are the bustling megacities of the cosmos, vast metropolises where thousands of galaxies gather under the grip of gravity, bound together in sprawling assemblies that can stretch for tens of millions of light-years. Picture New York City scaled up to cosmic proportions, with galaxies instead of skyscrapers, and dark matter weaving through the streets like an invisible infrastructure holding everything together. These clusters aren't just random gatherings, they're the endpoints of cosmic evolution, where matter has been funneled into dense knots over billions of years. The story of how these colossal structures form begins with the faintest ripples in the early universe. Those tiny density fluctuations from the Big Bang, amplified by gravity, slowly drew matter into growing webs of filaments. At the intersections of these cosmic highways, galaxy clusters began to take shape. Dark matter played the starring role, its gravitational pull creating deep wells that ordinary matter couldn't resist. Gas, dust, and eventually galaxies cascaded into these wells, piling up until they formed the most massive structures in the known universe. What's happening inside these clusters defies ordinary imagination. The space between galaxies isn't empty, it's filled with a superheated plasma, known as the intracluster medium, reaching temperatures of tens of millions of degrees. This gas glows so intensely in X-rays that it outshines all the stars in the cluster combined. Yet even this scorching inferno is just a tracer for something far more mysterious, the cluster's true mass, which is dominated by dark matter. Without this invisible scaffolding, the galaxies would fly apart and the hot gas would dissipate into the void. Clusters also serve as cosmic time capsules. By studying their distribution and evolution, astronomers can trace how dark energy has influenced the universe's expansion over billions of years. The sheer number of clusters at different distances, and thus different eras, acts as a barometer for how quickly structure formed in the cosmos. Too few clusters would suggest dark energy was weaker in the past. Too many might mean it's changing strength over time. These measurements are helping pin down the nature of dark energy itself, one of the greatest puzzles in modern physics. But perhaps the most dramatic role galaxy clusters play is as natural laboratories for extreme physics. Their immense gravity bends light so severely that they act as cosmic magnifying glasses, distorting and amplifying the images of galaxies far behind them. This phenomenon, called gravitational lensing, lets astronomers peer deeper into space than would otherwise be possible. Some clusters have even revealed multiple images of the same distant galaxy, warped into surreal arcs and rings, like reflections in a funhouse mirror crafted by spacetime itself. Collisions between galaxy clusters offer another window into the universe's hidden workings. When two clusters smash together at millions of miles per hour, their gas clouds slam into each other, creating shock waves that ripple through the intracluster medium. Meanwhile, the dark matter from each cluster passes right through, barely interacting. This separation between visible and dark matter provides some of the strongest evidence that dark matter exists and behaves differently from anything made of atoms. From their birth in the early universe to their ongoing dance with dark energy, galaxy clusters are more than just collections of galaxies. They're the universe's grand experiments, testing our theories of gravity, matter, and cosmic evolution on scales we can barely comprehend. Every time astronomers study one of these colossal structures, they're not just observing a static snapshot, they're reading a dynamic story written in gravity, gas, and dark matter, a story that continues to unfold across billions of years. The cosmic microwave background is often called the most perfect blackbody in nature, a near-uniform glow that fills the entire sky with only the slightest variations. But when scientists scrutinized this ancient light with unprecedented precision, they stumbled upon something unsettling. The temperature fluctuations aren't entirely random. Instead, they appear oddly aligned along a particular axis, as if the universe has a hidden preferred direction. Astronomers half-jokingly dubbed this the axis of evil, because if real, it threatens one of cosmology's most cherished principles, that the universe should look the same in all directions. At first glance, the alignment seems minor, just a slight preference for hotter and colder spots to line up along a specific celestial plane. But in a universe that's supposed to be isotropic, where no direction is special, even a tiny asymmetry is like finding a compass needle stubbornly pointing the same way no matter where you stand. The odds of this happening by chance are astronomically low, somewhere around 1 in 1,000. That's not quite smoking gun territory, but it's enough to make scientists wonder if they're missing something fundamental. Some argue it's just an artifact of incomplete data or subtle measurement biases. After all, our galaxy's dust and the solar system's motion can imprint faint patterns on the cosmic microwave background. Others suggest it might be a statistical fluke, a cosmic roll of the dice that looks meaningful only because we've sliced the data in a particular way. But if the alignment persists after accounting for these factors, the implications could be profound. It might hint at pre-Big Bang physics, a relic of some exotic phase of the early universe that left behind a directional imprint. Or worse, it could mean our entire cosmic neighborhood, the observable universe, is just a tiny, atypical bubble in a far vaster and stranger cosmos. The real puzzle is how this fits or doesn't fit with inflation, the theory that the early universe underwent a period of exponential expansion. Inflation was supposed to erase any primordial directionality, smoothing the cosmos into the uniform tapestry we expect. Yet here we are, staring at a possible contradiction. Could inflation have left behind subtle wrinkles, or does the axis of evil point to something inflation can't explain? For now, the anomaly remains unresolved, a quiet thorn in the side of modern cosmology. But that's the beauty of science. The moments that unsettle our assumptions are often the ones that lead to breakthroughs. Whether the axis of evil fades into statistical noise or forces us to rewrite the textbooks, it's a reminder that the universe still has the power to surprise us. After all, if cosmology were as tidy as we'd like, we'd probably be asking the wrong questions. For hundreds of millions of years after the Big Bang, the universe was a dark, featureless void, a cosmic sea of neutral hydrogen gas so thick it absorbed all light. This was the cosmic dark ages, an era when not a single star yet burned. But then, something extraordinary happened. In isolated pockets across the cosmos, gravity finally overcame the expansion of space, collapsing dense clouds of gas until nuclear fusion ignited the first generation of stars. These weren't like the stars we know today. They were monstrous behemoths, hundreds of times more massive than our Sun, blazing with such intensity that their ultraviolet radiation ripped electrons from surrounding hydrogen atoms. This marked the beginning of the epoch of reionization, the universe's great awakening from darkness. These first stars didn't just light up the cosmos, they fundamentally transformed it. Their fierce radiation began carving bubbles of ionized hydrogen, slowly clearing the fog that had blanketed the universe. Over hundreds of millions of years, these bubbles grew and merged like melting ice spreading across a frozen lake. Meanwhile, the first galaxies were forming, their collective starlight contributing to this cosmic defogging. The process wasn't uniform. Some regions ionized earlier than others, creating a patchwork of light and shadow that shifted as the universe evolved. What's fascinating is how this epoch connects to the universe we see today. The same ultraviolet radiation that ionized hydrogen also determined how galaxies could grow. In regions where reionization happened early, the intense radiation heated surrounding gas, making it harder for small galaxies to form, an effect that still influences the distribution of galaxies we observe now. This helps explain why some parts of the cosmic web are densely packed with galaxies while others remain relatively empty. The story of reionization isn't just about light piercing darkness, it's about the delicate balance between creation and destruction. Those first stars lived fast and died young, exploding as supernova that seeded the cosmos with heavier elements. These elements became the building blocks for future stars, planets, and ultimately, life itself. Without reionization, the universe might have remained an opaque fog, never giving rise to the transparent, structured cosmos we inhabit today. Scientists pieced together this epoch using some of the most distant objects we can observe, quasars whose light has traveled nearly 13 billion years to reach us. By analyzing how this light interacts with intervening hydrogen gas, astronomers can map how reionization progressed across space and time. New telescopes like the James Webb Space Telescope are pushing these observations even further, capturing glimpses of the very first galaxies that drove this transformation. The epoch of reionization was more than just a cosmic dawn. It was the moment the universe became recognizable. It set the stage for galaxies to flourish, for light to travel freely, and for us, billions of years later, to look back and trace the story of how darkness gave way to light. And in that story, we find one of the most profound truths of all, that even in the vastness of space, change is constant, and every ending is just another beginning in disguise. The universe is unimaginably vast, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. With so many planets orbiting inhabitable zones, the math suggests intelligent life should be common. So why, after decades of listening and searching, have we found nothing? No signals, no artifacts, no signs of cosmic engineering. This eerie silence is known as the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" One possibility is that we're simply alone. Life might be vanishingly rare, requiring such a precise combination of conditions that Earth is a cosmic fluke. Maybe the emergence of intelligence is like rolling a million-sided die, technically possible, but so unlikely it's only happened once. Even on our own planet, life took billions of years to evolve complexity, and countless species never developed technology. If this is the case, the universe's apparent emptiness isn't a mystery, it's just the way things are. But what if life is common and intelligence isn't the problem? Some theories suggest that advanced civilizations inevitably hit a great filter, some catastrophic barrier that prevents them from spreading across the galaxy. Maybe nuclear war, runaway AI, or environmental collapse wipe out civilizations before they can colonize space. If true, we might be precariously close to that filter ourselves. Alternatively, the filter could be behind us, some improbable step in evolution that few planets ever cross. Either way, the silence could be a warning. Then there's the unsettling idea that we're the first. The universe is ancient, but it took billions of years to create the heavy elements necessary for life. We might be among the earliest civilizations, with others yet to emerge. Or perhaps intelligence tends to arise at roughly the same cosmic time, meaning everyone is still too far apart to make contact. But what if the answer isn't about rarity, but invisibility? Advanced civilizations might have no interest in broadcasting their existence, or they could communicate in ways we don't yet recognize. Maybe they've transcended physical forms, uploading their minds into virtual realities where interstellar travel is irrelevant. Or they could be hiding deliberately, avoiding younger species until we reach a certain level of maturity. The universe might be teeming with life, but we're like ants in a rainforest, oblivious to the conversations happening far above us. The paradox forces us to confront our assumptions about intelligence and technology. Our search for aliens is based on what we think a civilization should do: build radio telescopes, launch probes, expand outward. But what if advanced societies follow entirely different rules? A civilization millions of years ahead of us might operate on scales we can't even perceive, manipulating dark energy or bending space-time in ways that leave no detectable trace. Ultimately, the Fermi Paradox is more than a question about aliens, it's a mirror. Whether the universe is empty or full, silent or buzzing with activity, the answer changes how we see ourselves. Are we a miracle, a warning, or just one voice in a chorus we're not yet able to hear? Until we know, the night sky remains both a promise and a riddle, reminding us that the universe's greatest mystery might not be its appearance, but who or what is looking back. What if everything around us, the stars, the planets, even the atoms in your hands, isn't real? Not in the way we think, at least. This is the core of the simulation hypothesis, the idea that our universe might be an artificial construct, an ultra-advanced computer program created by some higher intelligence. It sounds like science fiction, but some serious scientists and philosophers argue it's not just plausible, it might even be likely. The argument starts with a simple observation: our universe runs on rules. The laws of physics operate with mathematical precision, from the way electrons orbit nuclei to the way galaxies spin. These laws aren't just descriptive, they're computational, like the code underlying a video game. Even stranger, when we peer into the fabric of reality at the quantum level, things behave suspiciously, like a program rendering only what's being observed. Particles exist in fuzzy superpositions until measured, almost as if the universe is optimizing processing power by not rendering details until needed. Then there's the fine-tuning problem. The fundamental constants of nature, the strength of gravity, the mass of an electron, are balanced so perfectly that even slight changes would make life impossible. The odds of this happening by chance are astronomically low, but if the universe is a simulation, fine-tuning makes sense. A programmer could have set the parameters deliberately to allow for complexity, or even life itself. It's like adjusting the settings in a virtual world to see what emerges, a cosmic experiment running on hardware we can't perceive. But is there any actual evidence? Some researchers point to potential glitches in reality, odd quantum behaviors, mathematical patterns that repeat inexplicably, or even claims of déjà vu as possible bugs in the system. Others suggest that if the universe is a simulation, it might contain compressed or simplified physics at extreme scales, like the pixelation you'd see if you zoomed in too far on a digital image. So far, no smoking gun has been found, but the search is on. Experimental physicists have even proposed ways to test the hypothesis, like looking for signs of computational limits in high-energy particle collisions or anomalies in the cosmic microwave background. Critics, of course, dismiss the idea as untestable metaphysics. They argue that invoking a simulator doesn't solve the fine-tuning problem, it just kicks it up a level. Who fine-tuned the simulator's universe? And if reality is a simulation, why would the creators make it so vast and ancient, with billions of years of unobserved cosmic history? Wouldn't that be a waste of processing power? Yet the hypothesis persists because it touches on something deeper, our place in reality. If true, it would mean the universe isn't just stranger than we imagine, it's stranger than we can imagine. The line between science and philosophy blurs, raising questions about consciousness, free will, and the nature of existence itself. Are we players in someone else's game, or is the universe, simulated or not, all there is? Whether the simulation hypothesis is ultimately proven or debunked, it serves a valuable purpose. It forces us to question our assumptions about reality. After all, the greatest scientific breakthroughs often come from asking, what if we've been looking at this all wrong? And in a universe full of mysteries, that's a question worth exploring, no matter how unsettling the answers might be. Magnetic fields might be invisible, but their fingerprints are everywhere in the cosmos, woven through galaxies, tangled around stars, and even threading the voids between them. Unlike gravity, which pulls matter together in a straightforward tug, magnetism is a subtler force, acting like an unseen hand that guides and sculpts the universe's most dynamic processes. Take star formation, for example. In the dense clouds where stars are born, magnetic fields resist gravity's pull, slowing the collapse of gas and stretching the birth of stars over millions of years. Without this magnetic braking, stars might form too quickly, burning out before planets could even assemble around them. It's a delicate dance, one that ensures stellar nurseries don't rush their creations. These fields don't just linger in the background, they're active participants in galactic evolution. Spiral galaxies like the Milky Way are laced with magnetic fields that align along their arms, channeling cosmic rays and shaping the paths of charged particles. When galaxies collide, a spectacular event that reshapes entire structures, their magnetic fields twist and amplify, fueling colossal shock waves that can trigger bursts of new stars or even supermassive black hole activity. Imagine two giant whirlpools merging, their currents knotting into something even more powerful. That's magnetism on a galactic scale. Even the emptiest corners of the universe aren't truly empty of magnetic influence. The vast spaces between galaxy clusters, once thought to be devoid of structure, are now known to harbor faint magnetic fields stretching millions of light years. These cosmic filaments, weak as they are, act like interstellar highways, guiding high-energy particles across the universe and seeding galaxies with the raw materials for future stars. It's as if the cosmos is threaded with invisible wires, conducting energy from one place to another without us ever seeing them directly. What's truly astonishing is how these fields arise in the first place. They're thought to grow from tiny seeds, weak magnetic fluctuations in the early universe, amplified over eons by the motion of charged particles in plasma. Like a dynamo, the churning of gas in stars and galaxies can stretch and twist these initial fields, transforming them into the powerful forces we observe today. Even black holes play a role, their intense gravitational spins generating magnetic fields so strong they can launch jets of particles at nearly the speed of light, visible across the universe. Yet for all their influence, magnetic fields remain one of the least understood aspects of astrophysics. They're devilishly hard to measure, detectable only by their effects on light or charged particles. New telescopes and simulations are finally shedding light on their hidden role, revealing how these silent conductors shape everything from the smallest protostars to the largest galactic clusters. And as we uncover more, one thing becomes clear. The universe isn't just governed by gravity and dark matter, it's also written in the language of magnetism, a force quietly but profoundly shaping the story of the cosmos. For centuries, humans gazed at the stars and wondered, are there other worlds like ours out there? Today, we know the answer is a resounding yes. The hunt for exoplanets, worlds orbiting distant stars, has revealed a staggering cosmic truth. Planets aren't rare exceptions, they're the universe's default setting. Since the first confirmed discovery in 1992, astronomers have catalogued over 5,000 exoplanets, with estimates suggesting billions more in our galaxy alone. These aren't just random gas giants or scorched wastelands either. Many orbit in their star's Goldilocks zone, where temperatures could allow liquid water and perhaps life to exist. The methods used to find these distant worlds read like something from science fiction. There's the transit technique, where telescopes like Kepler and TESS watch for the telltale dimming of a star as a planet crosses its face. Then there's the radial velocity method, detecting the subtle wobble of a star tugged by an orbiting planet's gravity. More recently, direct imaging has captured actual light from exoplanets, while microlensing exploits the warping of spacetime to reveal hidden worlds. Each technique peels back another layer of the cosmic onion, showing us planets smaller than Earth, planets with two suns, even rogue planets drifting alone through interstellar space. What's truly revolutionary is how these discoveries reshape our view of planet formation. We once thought our solar system's orderly arrangement, rocky planets inside, gas giants farther out, was the standard. But exoplanets have shattered that assumption. Hot Jupiters orbit blisteringly close to their stars. Super-Earths fill the gap between Earth and Neptune, and some systems have planets packed so tightly their years last just days. This chaos isn't random, it's a testament to the dynamic, violent processes that shape solar systems. Dust and gas swirl around young stars, clumping into protoplanets that migrate, collide, and sometimes get flung into the void. The result, a universe where no two planetary systems look alike. The implications for life are profound. If Earth-like planets are common, then the ingredients for life might be too. We've already found worlds with water vapor in their atmospheres, planets with conditions ripe for organic chemistry. Some, like those in the TRAPPIST-1 system, even have multiple rocky planets in the habitable zone. Of course, habitability doesn't guarantee inhabitants, but it does expand the cosmic real estate where life could potentially take root. This explosion of exoplanet discoveries ties directly into the universe's grand architecture. Just as galaxies cluster along cosmic filaments, planets are the natural byproducts of star formation, woven into the fabric of stellar evolution. Every molecular cloud that collapses into a star carries the potential for planets, meaning the cosmic web isn't just a map of galaxies, it's a blueprint for countless worlds. Yet for all we've learned, the biggest questions remain. How many of these Earth twins actually host life? Are we alone, or is the universe teeming with biology? With next-generation telescopes like the James Webb Space Telescope analyzing exoplanet atmospheres for biosignatures, we may soon have clues. Each new discovery doesn't just add to our catalog of worlds, it refines our understanding of how ordinary or extraordinary our pale blue dot truly is. The next decade of cosmology isn't just about refining what we know, it's about rewriting the textbooks. At the forefront of this revolution stands the James Webb Space Telescope, a technological marvel already peeling back layers of the universe we've never seen before. But Webb is just the beginning. A new generation of observatories, both on Earth and in space, is gearing up to tackle the biggest mysteries: the nature of dark energy, the distribution of dark matter, and the first moments of cosmic dawn. These aren't incremental upgrades, they're quantum leaps in our ability to decode the universe's deepest secrets. Take the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. While Webb zooms in on individual galaxies with stunning clarity, Roman will pull back for the ultimate wide-angle shot, mapping the cosmos in unprecedented detail. Its surveys will measure the light from billions of galaxies, tracing how dark energy has stretched the universe over time. But here's the twist: Roman will also use a phenomenon called weak gravitational lensing to map dark matter directly. By measuring how unseen mass warps the light of background galaxies, it'll reveal the invisible scaffolding of the cosmic web in 3D, showing us where dark matter clumps, where it's sparse, and how it's evolved since the Big Bang. Meanwhile, on the ground, instruments like the Vera-C, Rubin Observatory's legacy survey of space and time, will scan the entire southern sky every few nights, creating a time-lapse movie of the cosmos. This isn't just about pretty pictures. Rubin's relentless observations will catch supernova in the act, measure asteroid motions, and even spot interstellar visitors passing through our solar system. But its real power lies in probing dark energy's grip on cosmic expansion. By tracking how galaxy clusters grow and move over billions of years, Rubin could reveal whether dark energy's strength changes over time, a clue that might lead us to its true nature. Then there's the European Space Agency's Euclid mission, another dark matter detective. Euclid will combine wide-field imaging with infrared spectroscopy, measuring not just where galaxies are, but how fast they're moving away from us. This two-pronged approach lets scientists distinguish between the effects of dark matter's gravity and dark energy's push, teasing apart their roles in shaping the universe's structure. It's like untangling two invisible hands molding the same piece of clay. Each leaves a distinct imprint, and Euclid aims to separate them. But perhaps the most tantalizing frontier is the hunt for primordial gravitational waves, ripples in spacetime from the universe's first trillionth of a second. Projects like the LightBird satellite and ground-based CMB-S4 experiment will scour the cosmic microwave background for faint polarization patterns, a smoking gun for cosmic inflation. If detected, these waves would open a window to energy scales 1 billion times higher than any particle collider, revealing physics that operated when the universe was smaller than an atom. The coming years won't just add data, they'll test foundational theories. Are we right about dark energy being Einstein's cosmological constant, or does it evolve? Is dark matter a single particle or a family of them? Does inflation explain the universe's smoothness, or do we need something even more exotic? Each new instrument is a time machine, probing deeper into the past while refining our vision of the future. And with breakthroughs like quantum sensors and AI-driven data analysis entering astronomy, the pace of discovery is accelerating faster than ever. What's at stake isn't just answers, it's the realization that our current models might be incomplete. Every time humanity has built a better telescope, we've found something that upends our assumptions. Galileo's lens revealed moons around Jupiter, Hubble's mirror showed galaxies beyond our own, and Webb is already uncovering galaxies too massive to exist in our timeline. The next wave of discoveries could be even more disruptive, challenging not just what we know about the universe's appearance, but what we think is possible. One thing's certain, the cosmos has surprises in store, and we're finally building the tools to uncover them. We've traveled from the quantum ripples of the early universe to the vast cosmic web, unraveling the forces that sculpted reality into the breathtaking tapestry we see today. Dark matter's invisible threads, dark energy's relentless push, the explosive birth of spacetime itself. Each revelation peels back a layer, only to reveal deeper mysteries waiting beneath. Yet for all we've uncovered, the cosmos humbles us. The more we learn, the more we realize how much lies beyond the edges of our understanding. Take dark matter. We've mapped its gravitational fingerprints across galaxies, yet its true nature eludes us. Is it a sea of undiscovered particles, or does it point to flaws in our theories of gravity? And dark energy, the phantom force accelerating the universe's expansion, is it constant, or could it shift over time, rewriting cosmic destiny? Even the cosmic microwave background, that snapshot of the infant universe, holds puzzles like the axis of evil, hinting at structures or symmetries we've yet to decipher. The beauty of cosmology lies in this tension between knowledge and wonder. Every answer births new questions, and every telescope we build reveals not just solutions but fresh enigmas. The James Webb Space Telescope's stunning images of early galaxies, they've upended expectations, showing structures too massive, too soon. The universe, it seems, enjoys keeping us on our toes. But that's what makes this journey so thrilling. We're not just passive observers, we're detectives piecing together a story written in gravity, light, and shadow. Each equation, each observation is a brushstroke in a masterpiece still being painted. And while we may never uncover every secret, the act of searching transforms us. It stretches our imagination, redefines what's possible, and connects us to something far grander than ourselves. So what's next? Perhaps we'll find dark matter's particles hiding in deep underground labs. Maybe gravitational wave astronomy will unveil echoes from the Big Bang, or an unexpected anomaly could shatter our current models entirely, sending us back to the drawing board. That's the adventure of science, it's never done. As we close this chapter, remember, the night sky isn't just a sight to admire, it's an invitation to question, to explore, to marvel at the fact that we tiny, fleeting creatures on a pale blue dot can even begin to comprehend the cosmos's grandeur. The universe's greatest gift isn't just its wonders, but the minds it shaped to seek them. Now it's your turn. Which cosmic mystery fascinates you most? The enigma of dark energy, the birth of the first stars, or something we haven't even discovered yet? Drop your thoughts below, and let's keep the conversation as boundless as the cosmos itself. Don't forget to subscribe, because the next breakthrough could be just an episode away, and you won't want to miss it. Until then, keep looking up. The universe is far from finished.